Good morning or good afternoon, everyone. Welcome to our Viessmann Solar Training Part 2, or Part 2. Not duh, but duh, Part 2. This is supposed to make you smarter, so we're going to give you, have an attempt here to have a look at today selecting and sizing solar thermal systems and piping arrangements. I'll be your instructor today. My name is Scott Bootlayer, coming to you live from our Viessmann Academy Langley office out here in Langley, BC, Canada. And joining me today for today's presentation is Mark Norris, Viessmann Academy Instructor Extraordinaire out of Waterloo, Ontario. Are you there, Mark? Good
I
morning.
am, Sunshine. How are you?
Or good afternoon. I'm doing fine, thanks. What an appropriate label there, Sunshine. Not sure.
Yeah, I
So
usually,
sure.
I usually call Steve Sunshine, but he's not here, so I'll call you Sunshine because
Oh,
it's
okay, by
so,
proxy. I
yeah.
get you. I'll take the name today. Yeah.
Yeah.
And it is a beautiful solar day out here, just so you all know. We always talk about the weather when we start these things up, and we got a great West Coast day out here. Nice, feels like summer out here already. So
Yeah. Not so much here. They're talking about a little bit of snow today.
wow. Wow. Well, I mean, you can use solar for space heating too, as we're going to have a look at. So that's that might be something that you might want to look into there.
So welcome, everybody. If you have questions during the presentation, there is a question and answer box in your tools. Please ask your questions in there, and I will try to get to them. And if there's something I need to hold on to the end, or if we get so many I can't keep up, we'll get Scott involved near the end of this. And I'll try to keep him on time today. If you guys were here last week, you know he was a little long-winded, so
I was rambling last week there. My
today.
apologies. Yeah.
So just in an effort of time, I'm going to give it back to you, Scott.
Thanks, Mark. Thanks very much. Appreciate you hanging with me here today, as well as you, the rest of you out there. As I mentioned, this is part 2, which means that we do have a part 1, and there's actually going to be another one next week, part 3. So the last week, what we just covered were basically just kind of basic concepts of solar. Just as a quick review, just talked about, the amount of energy that hits, North America, different regions of North America, what we can expect to harvest if we utilize solar there, as well as, if we're utilizing that energy, what type of applications can we use that energy for, right? For our daily requirements that we have for, heating heating water up, or pool heating, those types of applications. So those are the things we're going to actually get involved with today, sizing up those particular types of applications we talked about last week. And we also covered the collectors as well. So Viessmann North America, we have the 200 FM flat plate collectors, vertical and horizontal. And those are the collectors we'll be dealing with today as far as dimensioning and sizing these up for these different applications that we have here. So if you didn't take in last week's presentation and you're interested in that, or if you did take it in and you missed some of that last bit because we went a little bit long, I went a little bit long last week, then you can, that particular presentation will be archived on our Viessmann North America YouTube channel. So it's going to be available to you, just like this one here will be eventually.
And this last week's will be up in probably a day or so, because I just sent it up to Canada today.
Oh, perfect. So there you go. So another 48 hours or so, you should be able to take that first part in, and then probably sometime in the next 7 days, this particular presentation will be done in there. So this is essentially just, we kind of jumped into the basics of solar last week, and now we're going to take that information that we kind of discovered, and we're going to apply it. So this is going to be the application of all that information. So let's jump right into it here and have a look. We did talk about this little checklist that Viessmann has made up. So our solar guru in Waterloo, Ontario, Steve Royce, he does a lot of these documents for us, and he put this one out, and it always goes through, it's kind of a living document. It goes through some morphing, some changes there, but the body of it usually stays fairly consistent. And basically what we're looking at is, if we have we can send this out to you, you can get it off our website. It's, if you're in this type of, looking at adding solar to your portfolio, then it's not a bad idea to kind of have a look at maybe trying to find this so you can bring this to sites with you. And it's all about kind of gathering the information that's going to make designing that system a lot more simple, a lot more accurate for what you have out there. We always start off with like a project information, because the projects in reality, a lot of projects, I've been doing solar sizing with Viessmann for 13 years or so now, and a lot of projects aren't something that would happen right away. The guy's not going to call you and say, "I'm thinking about putting solar in next week." A lot of times, you're getting that contact, you're gathering the information, you're sending that guy a quote, a person a quote, and then it might be 2 or 3 years, and you might get a phone call about that particular project. So it's always good to have that information as accurate as possible here, because you give me a call and say, "You remember that project we did 3 years ago?" That's a little bit more difficult than, "Yeah, I've got this project number. Here's the information," and I usually pull that information up. We can update the pricing, and away you go. It makes a lot easier to find those projects in the that are a little longer in the queue. As well as the different applications we're going to talk about. There's all kinds of information here, depending on the different, domestic hot water, pool heating, or space heating. Just information that we need to size those or dimension those accurately is what we're going to do today. As well as, if we're sizing collectors, how many collectors can we put on the roof, what angle they're going to be, what deviation from south are they, all the things we talked about last week, roof pitches, if we're going to use the slope roof, all that information will be placed here. And of course, mechanical room, space, pipe distances, vertical heights from the collectors to the mechanical room, all that information is put in here so we can size things like piping, fluid calculations, and expansion tank, is all those things we're going to actually get through here today as we roll through. So we're going to kind of go through this, and then we're going to size that particular system up. So based on the information on that solar checklist, it gives the solar designer the information that they'll need to appropriately size whatever type of application you're looking at. So domestic hot water heating is what we're going to start off with here. I've kind of shaded that in a little bit of red here. The number of occupants, desired temperatures, what other things are going to affect the load of that domestic hot water heating system in that building. Things like if there's a recirc pump, domestic hot recirc pump on there. If there is any existing equipment that has to be basically integrated into that, and of course, any consumption information that might be available on site would be valuable. And you can see the stuff for pool heating, space heating as well, what we're looking for on those solar checklists. And of course, if we're dimensioning the collectors, what angles are going to set at, all that stuff I got up in the top right-hand corner would be something that we would want to have information on. So we'll jump right in here on the domestic hot water heating side of it. And this is the solar checklist on the right, a little basically a conceptual drawing of a domestic hot water system. And these little conceptual drawings are usually part of the simulation that we provide you. The performance simulation that would come from Viessmann would have sort of a conceptual drawing on there. It may not be as you're going to actually build it, but it gives you some information on what it might look like. And of course, in order to size up, we need to know what we really are looking for as far as the the amount of load we have. So the domestic hot water temperature is important. What type of hot water are we looking for here? Is it 40C, 50C, 60C? What are we dealing with there? How much of that temperature water are we actually using? And you can see that over here on the left-hand side. So in the dimensioning side of it, when we do the simulation, we'll tell you we used, in this case, 225 liters per day is what's required in this particular building. And we're going to have a temperature of 54 degrees C. So we're using every day 225 liters of 54 degree C water in this particular building. So that gives us our load. What we try to avoid, and then I'll kind of explain why, and we get this an awful lot, when you're engineering a system like a boiler and an indirect tank, or you're sizing, dimensioning a domestic hot water heating system for a building, we look at something very different than we do at solar. So if we were to so we don't want to have and highlight it here, we don't really looking for fixture counts or your peak load for the day as far as sizing your solar, because that tends to oversize the solar thermal system. So when I'm sizing a boiler and a tank or a battery of direct fire tanks or something like that for a building for the domestic hot water load, I want to know basically that I can cover when they're at the peak amount of energy that they're going to need, the peak performance of their system. So there's a profile of a building here over a 24-hour period. And if I can cover this load, I can cover all these other little peak loads here as well. If I've only sized this system for this, this little peak over here at, 8 o'clock or so at night, then in the morning here, somebody's going to lose, right? There's going to be somebody's going to jump in a shower or something that's not going to have enough domestic hot water because we haven't covered off that particular peak load. So as far as an engineer, designing a domestic hot water system, very critical bits of information here on those peak loads or fixture counts. With solar, what we're trying to do is we're looking at the whole profile. So not just this little peak up here, we're looking at the whole day, how much hot water is being used over that 24-hour period. And then we're going to dimension a collector system, basically, that's going to cover the operating hours. And that's the amount of time out of this 24-hour window that we have to basically gather as much of this overall energy over a 24-hour period as we possibly can without oversizing it and having some other issues. So this is where it's a bit different. We're looking at more of a 24-hour period than that little peak load in the system. So there's a bit of a difference there between the engineering and dimensioning of your collectors versus a boiler and an indirect tank. So how do we come up with that information over a 24-hour period? It's if there is a metering system, or if you have the ability of adding a metering system into a building for a week or so, what you can do there is gather that information about how much hot water is actually being used. And if you meter the consumption, then you have that direct information. It's factual. It's 225 liters per day. You're not going to oversize that system. It's a useful, obviously useful number to know, but not many systems out there are actually metered where you can actually see, this is, every day we're getting so many gallons of hot water being used. The other option would be looking at summer loads. So if you have, fuel bills for the summer, and your system basically is that, we have a boiler that's heating the tank up, and also space heating of the building. If we take the spacing of the building away and we're just basically supplying domestic hot water in the summertime, then we'd have a pretty good idea, based on those summer fuel bills, what that profile of that domestic hot water load is for that particular building. So another fairly accurate way or method of determining what that domestic hot water size requirement is going to be by looking at some actual historical information on the building and the load that's connected to it. If none of those things are available, if the system basically uses fuel for other things in the summertime that wouldn't be accurate to kind of pick it, we certainly don't want to oversize the domestic by adding in a non-domestic hot water loads to that the equation. The other thing we can do is estimation. So we have some fairly accurate estimation numbers here. These are over historical times and different tests and stuff like that for buildings, and based on the information that over data accumulated over years, between about 30 to 60 liters per day per person in a residential home, we find is going to be fairly accurate. We're not trying to oversize the system here. Obviously, we want to be a bit more conservative. And on multi-units, you'll see the numbers actually quite a bit lower, in 19 to 38 liters per person today, because it's a lot more accurate, obviously, to get an idea of 2 or 3 people in a building versus 200 or 300 people in a building, right? There's that dimensioning. So we're a little bit more conservative on those multi-units, not to oversize to a large degree. So you have these ranges, and it's about deciding where those numbers may fit. So if I'm looking at a residential home with a young family, I'm probably going to go a little higher on the the domestic hot water loading per day, closer to 60 liters per person per day. If it's a couple, a retired couple in that home, then I might look a little bit more conservatively on the how much domestic hot water they'd actually use. So I might be a little bit on the lower end of the scale there. And the same with the multi-unit residences. Obviously things like recirc pumps, the size of the tanks that are already there, I might be, adding a little bit more load to that, so I can cover off a bit more of their energy requirements. If everything is basically, a little bit more conservative, then I'm going to kind of go air down to the lower number there. So if there's a lot of turnover in the building and their occupancy numbers are, not at 100% all the time, I would tend to, look a little bit more on the conservative side of that and keep it down more towards a 19 liters per day per person than the bigger one. And if it's not a residence where we're looking at showering and washing dishes and et cetera, if it's commercial car washes or commercial laundromats, those sort of things, there's other kind of criteria that we look at. The number of cars and going through a car wash on average per day will give us an idea how much water consumption we have based on what we have there for sprays and stuff like that. The laundromats, the launder machines and their gallons of use per wash would be a good idea. Get a size of what the laundromat's going to do for us. All these things, again, when you start estimating, again, it's with solar, we like to be a bit more conservative. So we're not going to overestimate these numbers. It's always better to keep on the conservative side and work from that kind of that perspective. Oversizing, we like to do obviously bigger boilers, bigger tanks and all that kind of stuff. Bigger is always better. Not when it comes really to harnessing the sun. We want to be a conservative on there. The reason being is that once we put these collectors out there on the roof, we really can't turn them off. So they're active, they're gathering energy. We want to make sure that we size these appropriately for the actual amount of draw that we have here. Otherwise, we can run into some problems. So it's always better to be a little undersized than to be oversized in your system. So that's why I'm saying be conservative about those numbers. We have some of these quick sizing charts, and these are essentially to really kind of get the conversation started with your customers. It's not, I wouldn't be signing documents of performance based on what you see here as far as solar fractions and consumptions. They're really about a jumping off point. The simulations are much more accurate because they're going to be based on the regions and stuff like that. These are really generic in their in what they're trying to give you as far as information. But you can see very simple. Now, based on the consumption here that we have in the horizontal, each one of these is the percentage of energy that the solar is going to contribute. So 30% of the energy is going to be from solar. Up to 60% of the energy is going to be coming from the solar collectors over here. So we just draw, based on the consumption we have, draw a vertical line up to whatever solar fraction we want to grab, and then move over to the left, and you have your surface area in square meters over here. So 5 square meters would cover 60% of the domestic hot water load to make 200 liters of domestic hot water in this system per day. So that kind of gives you a real rough, and that would be based on an annual. We're not talking about December. We're talking about on a whole annual basis here as far as performance. And the same kind of thing for commercial applications. We have these little quick sizing charts. Again, it's about getting a feel for what it looks like. If you walk in and you're, in the previous slide there, and you saw, it was about 2 collectors, and you said that's going to be ballpark to the homeowner. That's going to be about $10,000. They can look at that and say that's not really what I'm looking for, or yeah, that sounds interesting. Let's talk more about it. Now you can start basically gathering information and getting a more proper dimensioning and quote done to kind of move that project forward. Same here. We look at consumption numbers and liters, and then brackets is in gallons, U.S. gallons. So the example here is 6,000 liters, a little over 1,500 gallons of water. We go up vertically until we hit the load line right here, and it tells us basically about 350 kilowatts of energy, somewhere around 1.2 or so million BTUs of energy is required. And we move over here to the flat plate collectors, and you would be looking at somewhere around 100 square meters, about 1,076 square feet of surface area for a collector sizing to give you the amount of energy to provide that amount of BTUs for your building for domestic hot water. So again, not like things that you would want to basically write out a proper quote for and basically do all the information. It's just a quick size to get a number out there and a ballpark about what the system might look like as far as sizing. You can also have a look at it on a monthly period. So we can look at this little equation here, basically a number of collectors that we need to cover the 100% of the domestic hot water load, 100% of the domestic hot water load for a particular month. We can look at the number of days that we're dealing with here. So based on the month that we're going to select, as well as the number of people, how many occupants are in the building, and their volume of hot water that they're going to use per person. We got some physics information here, the heat capacity of the water, density of the water, Your delta T is essentially the incoming water temperature versus the temperature rise that we're looking for. And of course, the overall efficiency. So efficiency of the system is based on, obviously with collectors, you got your collector efficiency. So 7% of the energy that hits the collector is being harvested. Heat losses in the tanks and the rest of the system is about 60%. So we put those numbers together. So the multiplier here is about 0.42 on our efficiency. And then we have the solar radiation that hits the Earth's surface during that particular month that we select here. Will be in basically megajoules, multiply it by 1,000,000 to get it just into regular joules, times the number of days divided by the absorber code. So y'all got that? Pretty straightforward. Basically, if you got the equation there, you can find all these numbers fairly easily. So we'll have a look at a couple of examples here. We've got a calculate the number here for July. How many collectors is it going to take to provide 100% of the energy for the domestic hot water system in this particular application? So what we're looking for here is we've got the number of days in July, 31. How many people are in that building and the volume of fluid that they use. Doing the math here for July as we move through, you can see that in July we get 21.8 megajoules per square meter per day. So that's sitting right there. We put all that stuff together and we end up with somewhere around just 1.97, or basically 2 collectors would cover 100% of the energy required for this particular building's domestic hot water load. So that's kind of how this little thing works. Again, we're using some information. Simulation would obviously be more accurate because it's going to deal with different fluctuations throughout the averages here. We could also have a look at this on the complete opposite and have a look at December. Now, usually when we size and dimension domestic hot water systems, we do exactly what I just did. We're going to size it for the summer months, not for the winter months, and I'll show you why here in a second. The December load here, so again, the same amount of days, 31 days, same amount of people, all the other things are the same. 2 things have changed. The amount of energy hitting the Earth's surface is now only 5.5 megajoules per square meter per day, and the delta T will be different here because it's going to be a little bit colder water in Boston in December than possibly in June. So I put it at about 5 degrees difference between the winter temperature and the summer temperature in December to July. So we have a 55-degree delta T here. So now instead of 2 collectors, we're up to about a little over 8, actually. I run it down to 8 collectors here to cover just about 100% of their energy requirement. So if we size the system for December to basically get all that energy that we can for the domestic hot water system, what do we do with the other 6 collectors in July? That's where the problem kind of arises when we size a system here, because the boiler, the BTUs of the collectors is going to change as we have sunny days versus cloudy days versus rainy days, etc. But the reality is having that dimensioning of oversized, we're going to have some problems in the summertime that we would have to deal with. So that comes down to kind of the scale of our systems. We looked at a residential system here, high solar fractions, a high basically contribution of the solar to the amount of energy that we need, versus larger scale solar systems, bigger commercial systems. As I mentioned previously, the reason why we do that is there's more volatility, more variability in commercial loads, on an annual basis, much more easy, much more accuracy in dimensioning smaller scale solar. So we tend to have a lot more kilowatt hours, a lot more energy usage in large scale systems, but we tend to basically drop that fraction down to a lower number here. So dimensioning tends to be, in comparison, the amount of energy tends to be a little bit lower than the smaller scale solar thermal systems that we have. And when we're trying to basically dimension a system, what we're kind of looking for here is there's a trade-off. We looked at that, that 2 collectors versus 8 collectors. If we design that system for December load, so that Boston domestic hot water system for family of 4, then we covered 100% of their solar for December, we would be way up here in the as far as a solar fraction, real high solar fraction, but the efficiency would tank because a lot of energy in the summertime there we can't use. We got to dump it. So that out here is not effective. You usually have a lot of issues with your systems. If we oversize, high solar fractions are always oversized types of systems typically. And essentially we have to deal with that, or we start having problems with the system, with overheating, more maintenance, lower life expectancies of these systems. So we tend to dial the solar fraction down here a little bit. We don't want to go too far down the curve, because then we end up with a real high efficiency and a low solar fraction. What you end up with is essentially a system where you're sucking all the heat out of that collector, but they're at such low kind of diluted temperatures that you don't really contribute a whole lot to the system overall as far as the yield. So you get a lot more efficiency, so a lot more transfer of the energy hits the collector surface, but it's really at a really diluted amount. So the returns tend to be quite lower on the high efficiency systems with low solar fractions. So what we try to do is kind of dial right into this area. So the kind of the intersection point of fraction and the efficiency when we do our simulations, we're targeting this area here. We kind of get the best bang for your buck, where the system is not going to be overheating and problematic, but you're also getting a good amount of that efficiency or a good amount of the fraction out of that system on an overall basis. So that's kind of our target area. With our collectors, the 200 FM collectors, we tend to kind of go more towards higher fractions here because the collectors are limited in temperature. That's kind of the big magic behind the 200 FM collectors, is they are a much lower maximum supply temperature or stagnation temperature than collectors that are not don't have the ThermProtect type of coating on them. Traditionally, your flat plate collectors could be up over 190 degrees C when they get to stagnation. Viessmann ThermProtect collectors hit about 145, and that's basically when they turn into an emitter. And so their max temperature is about 145 C. So safely, we can kind of oversize that system without worrying a whole lot about, and with some minimal amount of kind of control changes, without having to worry about putting a large heat dump system in there, added cost, without a whole lot of return or a lot of value on that particular cost. So we can increase solar fraction, lower that efficiency a little bit, but it's free heat after all that we're grabbing off of the sun. So more is going to be better here overall. Keep that fossil fuel system from operation, and keep the solar giving us a larger amount of our energy year round. So that's kind of where the magic of the FM kind of sits, is we kind of we can go a little bit larger on that dimensioning without having a lot of the issues that previous systems would have. So once we have the collector sizing, kind of an idea how many collectors that we need to cover those loads and what our fractions and stuff of that are looking like, we want to make sure that we dimension the rest of the system around what we have up on the roof or on the ground or sitting on the wall, wherever these collectors might be. As we talked about, there's lots of different ways of mounting the collectors, and Viessmann have racking for all those different applications, depending on what you're looking for. So if we were to throw 3 collectors up on your roof, and looking at that, what we're looking for basically is we don't want to go basically have only enough tank storage here that we get, to about 2:30 or so in the afternoon, and our tank is now sitting at 70 C. It's essentially, it's at max. It's basically not calling it for any more heat. So now we go from, 2:30 until, 5:30 or whatever, without any load on the collectors. And this is where you're going to get into some problems, right? So now we've got nowhere to dump the heat. These collectors are still gathering energy, and we can get into some issues with what we call stagnation, steam back formation in this particular area in red. So the idea is to basically ensure that we dimension correctly for every square foot of collector area or square meter collector area on the roof. We have a certain amount of gallons or liters sitting inside of this tank. When we have that information, this is often the problem, is we oversize the collector area and the tank amount of storage dedicated to the solar is not sufficient enough, and we end up having a problem. So properly sizing the storage for the solar is a important part of ensuring that we have a good solar fraction, as well as keeping that efficiency at a relatively high number. And again, that's dedicated solar storage, which means that, if the boiler can heat this tank up, or we got a geothermal system that can heat the tank up, we don't want to have, basically that's not dedicated storage for the solar. We want to make sure that there's enough energy basically in this tank that throughout the whole day, these collectors are operating, that we don't basically hit this tank set point and shut the solar pump off, right? So some dimensioning for you here. Again, a little bit different between a residential and a commercial application. With residential, it's 50 to 65 liters per square meter, a little over, a little under 1.25 gallon to 1.6 gallons per square foot. Usually equates to about 30 to 40 gallons for every collector. So 30 to 40 gallons of storage in a residential application for every collector up on the roof, every FM collector on the roof would be a good number to kind of look at. And with commercial, it's a little bit smaller, 22 to 31 gallons. Reason being, obviously, with commercial, a little bit bigger tanks. If you think about your system, we've got to think of these tanks like batteries, and of course, the collectors as the charging station for those batteries. The more you drain those batteries, and of course, the charging unit here can recharge those batteries on a daily basis, the lower the volume of that tank can be. So if I'm constantly draining that tank down, I could go to a smaller number, 31 gallons per collector, for instance, in residential versus 40. If I have a lighter draw rate, then of course I'd have to go to a slightly higher number there. So it just depends on, when the water is utilized, and of course we're going to size that tank appropriately. With commercial application, a little bit smaller, you can think that, with a commercial run, you're probably going to have more spread out loads. So some people are, doing the laundry in the morning. Some people are doing them in the afternoons. Some people are showering in the morning. Some people are showering at night. So you have a lot more consistent, a lot more draw throughout the whole day, which means we're draining that battery and we can recharge the battery with the solar as we move through. So we can have a little bit lower number here. Also, things like recirc pumps and stuff, probably more recirc pumps, bigger pipe sizes, more losses in the commercial piping system. So of course that reheating of those tanks is obviously you could utilize the solar for that as well if things are piped correctly. And of course that would allow us to use a slightly lower amount of tank capacity for those applications. So just some numbers there for you to look at to make sure that we dimension the systems appropriately. So just some rules of thumb here for residential applications. Typically, 1 to 5 people in a building. The first one here, one collector, you can see we're at 40 gallons for that one collector. If we went to 53 gallons, we would have a higher efficiency, obviously, because we'd have more capacity for that energy to be stored, and as well, we would basically have a slightly higher fraction as a result of that bit more storage. 3 to 4 people per day. We're at 2 collectors here now, and you can see, 2 collectors, 79 gallon tanks, so 40 gallons per collector. 5 plus, we've got 3 collectors, 120 gallon tank. We're at 40 gallons per collector on that particular system as well. So as the dimensioning on the roof increases, so does the dimensioning in the mechanical room. That's for proper solar design. When you get into commercial applications, we have that 0.85 to 1.23 gallons per square foot of collector area. So we've got a buffer tank here and a flat plate heat exchanger, which kind of you see a lot more of these in commercial applications versus a big battery of tanks. You've got 20 people per day, 200 gallons of domestic hot water being used. We've got a 265 gallon tank with an appropriately sized heat exchanger for that. 40 people basically. So for every 200 gallons, it looks like we're getting about 1,000 liters of tank sizing here. So just kind of a dimension that we can look at. So just some rules of thumb, and these are just to get you kind of on that budget side of the system, kind of understanding the number of collectors, the size of the tanks, and et cetera. Give you some budget information there so you can move through those domestic hot water loads as far as some decent, accurate estimations. If we move on to dimensioning for pools, so moving into the pools application, an outdoor pool, for instance, we start out with here, and this is kind of the portion of the solar checklist that deals with pools. Indoor pool, outdoor pool is one of the things that's asked here. But if you look at the profile of a pool that's not being heated by solar, so this is the red little bar graph right here on the right hand side, you can see that the profile as we go through the summer here. So we start off just the sun shining on the pool, you have this base temperature being created. Solar is not really going to change the profile of that. You see the orange here is when we add the solar dimensioning to the system here, but it does increase the temperature as we add the solar in. And that amount of temperature here is directly related to the ratio between the pool surface area, so the length and width here, and the absorber area sitting on the roof. So if we look at a system, we've just fill in a little bit of the information. Outdoor pool, May 15th to September 15th. We got a 30 by 15 by 4 foot average depth. Equates to somewhere around 13,466 US gallons of water sitting in that pool. And what we're looking for here, basically, the starting off point is typically dimensioning. We start off with looking at the area, 30 by 15, 450 square feet, multiply it by 0.5. And this is a good starting point for the amount of collector surface area, absorber area, I should say, that we should start with. 225 square feet of collector absorber area up there on the roof. So if we look at this, what does that really equate to? If we have a ratio between the absorber area and the pool surface area, so 50%, 0.5 here, you ride up the curve until you hit the mark right here. And over this way, we're a little over 5 degrees Fahrenheit per day, a little over 3 degrees C Fahrenheit per day is what we can average temperature increase in that pool. So as we heat the pool up from start to finish, we can expect to increase the temperature in the pool by about 5 degrees during that particular operation. Interesting to note how many BTUs it takes to actually raise this particular pool 1 degree Fahrenheit. So we took it at 13,466 gallons of water, multiplied it by the weight of a gallon of water. We can basically look at about 172 pounds of water. We want to take it up 1 degree Fahrenheit. So we need about a little over 12,000 BTUs for every degree that we want to basically pull that pool temperature up. So that's important to kind of note that if for every degree we increase the pool temperature, we want to and make sure that we don't lose that degree overnight. And a big part of heating your pool with solar is to have that pool covered at night. And that basically any gains we make here, if we don't cover the pool, guess where those gains go? They basically get sucked out of the pool by the atmosphere. You're going to have some evaporation and stuff like that as well. So if we don't cover the pool, we're going to essentially be dropping the pool temperature down at night and trying to pick it back up again with solar during the day, only to drop it off again at night. So the pool cover helps a lot to kind of, you grab that energy, you want to keep it, you need to cover it. The other area that we have a lot of losses would be in makeup water in your pool. So any evaporation is going to mean fresh water that's going to have to be reheated from the entering water temperature up to that usable pool temperature. And as we increase the pool temperature in comparison to the outdoor air temperature, there's going to be some more evaporation there as the temperature, especially when we look at the nighttime, when the pool is not covered. And of course, that higher temperature now, or that heat just gets evaporated to the atmosphere. Infinity edges, so infinity pools, beautiful edges on them, but of course that cascading of water creates more evaporation. Number of swimmers will also basically increase the amount of evaporation in the pool, and more makeup water to be added in there. So some of those loads there are part of this whole equation there to come up with an accurate number on how many collectors and what the performance of those collectors are going to be in that particular system. When we add the pool heating and domestic hot water together, multi-load systems, what ends up happening is a couple of things. Obviously, you're going to heat the pool using solar energy, but when the pool is not being used in the wintertime, the collector array is now quite a bit larger. Think about that Boston, with 10 collectors versus 8 collectors versus 2 collectors in July. Now we've got those. Now we have that large amount of collector array. So we're really going to boost up the amount of domestic hot water coverage for this system as we operation. So if we look at, a typical pool heating application, we want to go summer bias, which means we're going to tilt those collectors a little bit lower to the horizon so the sun can hit them at a 90-degree angle more in the summer. So instead of a 43 43, 44 degree angle, which would be the latitude of the location here in Toronto. We're going to drop it down 15 degrees for instead of this, we're going to angle it at about 30 degrees. And you can see in 30 degrees, we increase the amount of solar energy available here, little orange line, right? We see right here, but we drop a little bit on the shoulder season. So when we stop heating the pool, we actually lose a bit because, of course, the angle here is not optimal for winter operation. So we have a little bit of that heat basically dissipating directly off of the collectors just by optical losses. That's going to help basically to make sure that we're not oversized for the domestic hot water load here in the winter. So what happens is we get a good pool solar fraction, but the domestic hot water solar fraction typically goes from, your 50 to 60%, 80, 90% plus when we add that to the system. So a nice combination when we have multiple loads here where the control of the system here now can kind of look back and forth between, can I heat the pool? Can I heat the domestic hot water? And basically turn on whatever pump is to maximize the efficiency of these collectors in operation. On indoor pools, very similar to if you want to calculate how many collectors that we would need. Again, it would be more of a summertime basis for this, unless you've got some loads in the winter that you can utilize. The calculation is basically the same as the domestic hot water that we looked at. How many collectors we're going to need for a particular month of the year. So same kind of idea here for the pool loading. We look at the number of days in the month. So if we look at June, which is a good time to basically size up a collector system for indoor pool, we see here we're back in Boston again, 22.1 megajoules per square meter per day. We see the how many gallons of water we're going to have to basically heat up here, number of days in the month. We got 30 days. Our physics here as far as density of water and the specific heat capacity. And of course, our efficiency here, it's a lower number. The efficiency is actually a little bit higher because the temperature of the pool is a bit lower, which means the collectors will be a little bit higher in efficiency in their operation. And of course, the delta T is a little bit lower, bringing from inner wiring temperature to usable pool temperature. So when we look at this, basically throw the numbers in here. We come up to, June, an indoor pool this size, about 8 collectors would basically heat the pool to the temperature that we had, we were looking for there. So just a nice way of basically estimating the number of collectors. Again, not as accurate as if we put this into a simulation, but it gives you the ballpark here now that you can start talking to that decision maker to say, this is kind of the ballpark, are you comfortable with this type of budget number? And we look at solar space heating support. It's probably of all of the applications we looked at, this is the most challenging for solar because we look at the graph over on the right-hand side. December, those months for heating, the sun is, much lower the horizon, which means that we have less hours of sunlight. So we have less time to basically collect that and harvest that energy. It's also the sun is a little farther away from the earth at this point because of the tilt of the axis, which means that the energy is a little bit more diluted, right? Not as quite as intense as it is when it's basically a little higher in the sky, like in June. So we're kind of working at a bit of a disadvantage in the wintertime for harvesting the energy. And also the amount of energy we need is where the amount of energy available in the sun is going to be at its lowest. So when you need the most amount of heat is when, of course, the solar is going to be at its lowest amount. That's why you have to heat the building. So things that we look for, obviously, we want to target return temperature for space heating systems, which means this is the lowest temperature in this whole system during operation is going to be returning back to the boiler. And of course, we want to make sure that whatever piping we have connected to the boiler here is done so that this is going to be the lowest temperature that we can get. So any mixing valves and stuff like that, we're not diluting any of that and raising that temperature up to a higher temperature where the solar may not be available. Basically, the idea here is that whatever we have stored in this tank here for space heating has to be able to get to a temperature higher than what we see here. When that happens, this little diverting valve here is now going to move over and the return is going to go through the tank. And as soon as that happens, we are starting to get some solar fraction for space heating. But if this tank never gets the temperature, of course, the diverting valve never moves, and we never use whatever kind of heat is sitting inside this tank is actually never being used to heat the building. So how do we achieve that temperature? The best systems are low temperature heating systems, so radiant tubing systems, so high mass radiant systems where you're going out here at a low temperature, which means the chances of this return temperature is going to be lower than what's in the tank is going to be more potential for that to happen. So it's particularly on the shoulder seasons when you have need a little bit of heat during the evenings and in the mornings and stuff like that. This would be a system where you would actually get to a point where we get some usable temperature in this tank. Same with high delta T systems, where we're coming out at a high temperature, but because we got such a high temperature drop across the load here, that the return temperature comes back where we might get to a usable temperature in the tank compared to the return. Typically in the shoulder seasons, that's more potential in high delta T systems. The idea here is the strategy is for residential systems, oversizing is to target a low space heating solar fraction. So we saw this when we looked at stuff last week where, conservatively what we would usually do is if we needed 2 collectors for domestic hot water and we wanted to add some space heating supplement to a building like this, we might put 4 collectors instead of 2. So we oversized by a factor of 2 and instead of a much larger factor. So a lower solar fraction, but there's potential there that we may not have to add things like heat dumps, et cetera, for our FM collectors to add and increase the cost and lower the value of the system in that particular event. So just some things there. Be careful with solar space heating. Really, those design temperatures. If you're trying to heat baseboard and fan coils, you're just not going to get to usable temperature in that tank for those types of applications unless you design real high delta T systems in those loads. So as far as the tank dimensioning here, you get much larger tanks for solar space heating, 2 gallons per square foot, 80 liters per square meter. So bigger amounts of energy. The reason being is that we need to harvest for a rainy day. So we're kind of storing the energy for the point in time when we're going to need that energy for operation. So think about those solar, those sunny days in the late spring and early fall and into the mid fall and kind of mid spring, where you might have enough really nice sunny days, but it gets colder at night and the mornings are a bit crispy. If we can gather the energy during the day, we can utilize that energy in the evening or in the mornings the next day. So a lot larger storage tank. We'd also over dimension the domestic hot water tank here for a little bit, which would allow us to not only in the wintertime basically dump energy, or summertime dump energy into the buffer tank for the space heating, but also we have the direct heating of the tank itself here. If we oversize this a little bit, we've got a benefit there where if you look at this little pink line at 60-degree angles, a little bit higher peak pitch on our collectors for space heating bias, the reason you'll see is that little purple line here on either side, you get a little bit more energy out of the collectors in the shoulder seasons by this high pitch. Oops, sorry. But you also lose in the summertime about 15+% of the energy that would hit those collectors because the collector is at such a steep angle. So we have basically a heat dump right here, natural heat dump, by just pitching the collectors a little bit steeper for space heating. So a smaller, oversizing of the dimensioning of the domestic water tank will help to basically offset the number of collectors here by adding a little bit more storage in there for the domestic hot water. So a combination of this added to the buffer tank here for heating up with our FM collectors would mitigate having to use things like, fan coils and other heat dumps to get that heat out of the system in the summertime. So those are some information basically on dimensioning. So this is kind of the things that we would use for quick sizing of those different loads. And when we get the solar checklist, we go through an actual proper simulation program, which gives us much more accurate annual information. We can literally break it down like week per week if we wanted to on an annual basis. But typically we spread that over 365 days a year and give you an idea of performance over those 365 days a year for all those applications we just looked at. So when you send us a checklist, we kind of do all that stuff automatically for you. I just wanted to give you a little bit of information there to kind of try to make sense of all this the solar loading and application. So once we have the dimensioning of the collectors and what we're looking for as far as size and to cover our domestic or pool or space heating loads or combinations of those, it's about how these collectors can fit on the roof now or on the wall or wherever we're actually going to locate the collectors. And we talked about this last week. We can put up to the type of collectors we have allows us to put multiple banks of collectors together like this in a single array. They're all piped in parallel. So pipes come down and pipes come back up again. So this way we can have, coming in on the bottom and out on the top on the same side. You can go from 1 to 10 collectors in this configuration. So basically same side of the collectors, supply and return, capped off on one side. Once we go past 10 collectors, we could go up to 12 piped in a single array like this, which is quite unique. So returning in on the bottom and supplying here out in the top. The hottest temperature is going to be at the top of the collectors here. We're going to talk about things like sensor locations and stuff next week, but just kind of getting an idea of where we're going. And once we have our system laid out here, we also have a selection as far as the operating mode of our system. So how are we going to basically operate these systems? You got a low flow operation, or a high flow operation, or a match flow operation. My suggestion is you kind of look at what you're looking at as far as the amount of collectors. You select either low flow or high flow. Ensure that you've got good operation, and then start looking into tweaking, because match flow basically gets into just extracting a little bit more efficiency, because now the system is going to match the load based on the energy on hitting the collectors at that particular point in time. Trying to basically get the temperature rise to the collectors a little bit better. So if it's a really good solar day, you're going to get a little bit higher pump action. A little bit less ideal solar day. A lot of diffuse radiation, a lot of cloud cover, that sort of stuff. Then maybe the pump slows down a bit in those days. So it kind of matches the intensity of the energy hitting the collector. Where the other ones are more fixed, we low flow or high flow. So tweaking after we kind of certify that the system is in operation, either one of these two, we can go to a match system. Be very careful with match flow systems on systems like with evacuated tubes, those types of applications. If you can get into match flow, if you drop that flow rate too low, you get into laminar flow, and if you get into that type of flow rate in a evacuated tube system, the temperatures can spike quite dramatically, and you can get lots of issues there on that. So just kind of a little bit of word of the wise on that particular operation. But certainly, once you move into this area, you can really kind of pull the efficiency out of that system. So if we have a low flow operation, what does that mean? Basically, with low flow, we have 0.01 to 0.012 gallons per minute per square foot of collector area that we have, absorber area that we have up on the roof. So for every collector, we got 25 square feet of collector absorber area in each collector. So basically we have between about 0.25 to 0.3 US gallons per minute per collector in a low flow application. So pretty low flow rates here. Pressure drops between 28 and 31 inches a water column in a low flow application. High flow, and I kind of identified low flow in red because you're going to have higher temperature in a low flow application. You're going to have more temperature rise across the collectors because we are slowing the flow down. So more of a rise across the collectors. With high flow, we are basically having a little quicker flow rate across the collectors, which means they're blue, a little bit cooler as far as the supply temperature going out. But the range is bigger, 0.3 to 0.63 gallons per collector. So flow rate, US gallons per minute per collector. So basically pressure drop 31 to 110 inches per collector. So because the collectors are piped in parallel here. So this is how you're piping your collectors. They're all in parallel here. When I have a bank like this, I just have to basically pick the pressure drop of flow rate across one of these collectors to identify what the pressure drop in that whole bank of collectors is going to be. If they were piped in series, so if I was coming in here, out, back up here, down here, out, up, then I'd have a massive pressure drop that I have to calculate across all those collectors. So if we pipe them in parallel, as we see here, which is how we show them in the manual. Then, of course, the pressure drop, your calculation is just for one collector in an array like this. So typically, when you're into a system, high flow, we typically limit to about 10 collectors. So after about 25 square meter of collector area, we are going to go to a low flow application. But high flow basically reduces the losses. So you get a little bit higher efficiency on the collectors themselves. So we can go up to about 6.3 gallons per minute with the 10 collectors here, you can see. So whether we pipe them on the same side or different sides, you can see that what we'd be looking for here. So high flow operation. So basically, if we have 8 collectors, you're going to pipe them this arrangement. With high flow, if we go up basically 9 to 10 collectors, we're going to go basically in on the bottom and out on the top like this for that. For low flow, once we go past about 25 square meters, we recommend this type of application. The reason being is that you might get a higher temperature spread across the collector, so a little lower efficiency, but you also have a much smaller pump in low flow applications, probably smaller piping. A lot of the components in your system dimensions much smaller, which means the cost of the system capital wise is going to be much less as well, which basically and essentially the capital cost savings versus the efficiency loss, the savings in the equipment is greater than the loss that you're gonna have here. So it's a much more favorable system. Smaller pipe diameters, etc. So 10 to 12 collectors, you can see anywhere between 2.5 to 3 gallons a minute. 12 collectors, 3 to 3.3 gallons a minute. So some real low flow rates there, which means your pipe sizing is going to be quite a bit smaller. Even though you think of this as a massive array, it really is not that big of a pipe system or a flow rate that we're looking for. When we put multiple collectors together, so multiple banks, multiple arrays of collectors, pretty much always going to be a low flow. And you might have reverse return type of systems as we see here, or you could also have direct return and with flow setters on each bank of your collectors here. It depends. Generally speaking, this balances the system. The flow setters would balance the system direct flow a little bit more accurately, in my opinion. But it depends on the amount of exposed piping. And we'll look at that in a little bit when we talk about insulation. So with these systems, like I say, for larger installations, high flow is not recommended, as this results in bigger pumps and larger pipe sizes, increased costs. Those budget numbers, those quotes start coming out much larger, probably a limited amount of success when you get the decision maker say, yeah, let's go for it. So once we have the flow rates figured out there, what we're looking for, we can start dealing with sizing of the pipes. Just a kind of blurb here, we talk about with our systems, closed loop solar thermal systems with risk of freezing in the piping, we're going to use a water glycol solution. Of course, the pumping requirement, pump head for these systems are going to be quite a bit more in colder temperatures, so almost double the pump head requirement for a water glycol system at down around the 0 degrees to 10 degrees. But in operating conditions, in this area here, where we generally speaking are operating our solar pump, there's just a minor difference between the viscosity of water and the water glycol. So it's not something that we would be so concerned about in our systems as far as operation. So kind of thinking about considering when those pumps are going to operate, we're going to be in this particular area of our area of operation. So can we use different types of piping? PEX, for instance, not a recommended. PEX doesn't have enough pressure rating. We can be up to 60, 70, 80 pounds in our systems here, and up to 145 C as far as the operating temperatures or temperatures in the collectors. So PEX isn't really a recommended system. So I wouldn't recommend you use PEX. Oops. Solar thermal system, what we recommend for piping here would be basically coppers, your typical plumbing copper for space heating systems, so as well as stainless steel line sets. We have these available for high flow. Smaller dimensioning systems, we have these 1/2-inch stainless steel line sets available as well, which are basically, there's no solder or anything else like this up on the roof. It's all compression with those types of components. And then of course, steel pipe, we have available. You could use steel pipe here as well. Avoid anything galvanized or anything with a galvanized coating, because glycol will basically the galvanized coating don't mix very well. You'll have some issues there. So avoid any type of potable piping, galvanized piping in your solar thermal closed loop systems. So when we're sizing out the system here, so let's dimension something out here. So we've got we just started installing this system. We just got here in time now to size the rest of the system out. They got the collectors up on the roof. Now they're wondering, what do we need here for pipe sizes? What are we looking here for expansion tank sizes and all kinds of other things. So we've got the 15 collectors here. Hopefully they figured out the storage volumes down in the mechanical room. We'll look at this in two different ways to kind of have a look at, which way is the most successful way of quoting. Low flow operations, certainly 15 collectors, that's right in the low flow kind of wheelhouse. Outside of the high flow, and you'll see here why in a moment, but we'll do the math on it to show you what we're looking at here. Another thing important, kind of dimensioning wise, just your collectors are usually higher than where the air vents are going to be in your system. There are usually air vents in up on the roof here, but we usually shut them off after commissioning, so they're not sitting there allowing glycol to escape, dropping your pressure. We usually shut those off. So any residual air in your system, it has to now be driven down into your mechanical room to get rid of that air. So very difficult for it to do. So over dimensioning the piping here would have that impact. So it's one of the reasons why the lower flow is a better way. We tend to keep a smaller pipe diameter. So we have a 0.25 US gallon per minute per collector versus a 0.5 on the high flow system here. So a pressure drop, 28 inches in the low flow, and we got 90 inches here on the high flow. So we got our pressure drop through our collector systems up on the roof here. So we've got basically 90 inches on the high flow, 28 inches on low. And we're looking for just like any other hydronic system, what we want to do is keep the pipe velocity reasonable. So we're trying to basically get into that kind of 1.3 to 2.3 or so feet per second of velocity. So keeping that, keep a nice turbulent flow in that fluid as it's moving through the system. So we got good heat exchange. So we're sitting here, 3.75, so kind of in this area here. Looks like we got 1-inch pipe, and on the blue, the high flow application, 7.5 gallons a minute. We're gonna in between these two areas, so we're gonna about sitting around 1.25-inch pipe to start on both of these. So right off the bat, low flow, we're a full pipe diameter smaller. So depending on what we have there for piping, could be some significant cost savings right there in the different sizes of the pipes. Also fluid, how much fluid is it going to take to fill up the 1-inch pipe versus 1.25 inch? Well, we're using type L copper, and you get basically for every foot of type L copper, about 0.043 gallons of fluid in 0.065 gallons of fluid in an 1.25-inch piece of pipe. We know from our solar checklist here, which dimensioned the mechanical room space available, we have basically 80 feet of piping between the collector and the mechanical room. So that's one way. We double that for 160 feet, means we've got about 6.9 gallons of fluid in the 1-inch pipe, 10.4 in the 1.25-inch pipe at 160 feet. In the collectors, you got 15 collectors, and the SH2F collector holds 0.63 gallons of water for every collector. So multiply that by 15. Our 9.45 gallons is going to be basically represented in all 15 of these collectors. 3.75, 7.5. So what else do we have for fluid? Let's have a look here. We have heat exchangers, right? We got a heat exchanger in the tank, heat exchanger here for the pool. That's going to have an amount of fluid in there. So we got 3.5 gallons between those two. We have pumping stations. So one here and another pumping station here. So they'll have air separators and stuff. So there'll be some fluid sitting there. So 0.5 gallon or so of fluid in the pumping stations. Expansion tanks, we got 0.7 gallons in the expansion tank. And we'd add in anything else that's basically going to have storage of our glycol to make sure that we have enough glycol to fill that system. So additional fluid in the system for this is 4.7 gallons. So if we do the math here, 9.4 times plus 6.9 plus 4.7 is 21, a little over 21 gallons in the low flow system. We're at about 24 gallons, a little almost 24 and a half gallons in the high flow system with a bigger pipe. So a little bit more fluid required, which makes sense in that particular system. So we got the amount of fluid we're looking for. We got the pipe sizing. Now we have to look at the pressure drop in there. We need to size up our circulators. So we have 160 feet of pipe, and we've got 3.5 gallons a minute in that 1-inch pipe, 7.5 gallons a minute in that 1.25-inch pipe. In the low flow application here, so remember in the collectors, we had about 28 inches, which equates to about 2.3 feet of pressure drop going through the collector. On the high flow, the collector was 90 inches of pressure drop, or about 7.5 feet on the high flow. If we basically subtract our 60 from our 56 here, we get basically our pressure drop in our piping, 3.9 feet, plus times 2.31 to give us basically our feet of head. Sorry about that. 3.9 is our PSI. 2.3 is basically your feet per PSI. So basically 9.1 is our feet of head. Added to that 2.3, you get overall pressure drop in the piping and the collectors of 11.34. In the high flow, we're at 20.44. So we got more flow rate, and we've got a higher pressure drop with a bigger pipe diameter in the high flow rate system. So we can size our pumps now. We got 3.5 and 7.5, and we got the pressure drops. So we look at our tables here. And of course, the first one here on low flow, 3.75 at about that a little over 11 feet ahead. We're underneath of the performance of this particular pump. And of course, the higher flow, 7.5 gallons, a little over 20 feet ahead. Of course, we're just under the performance curve of this pump here in the blue. And we still have things like expansion tanks, heat exchangers, stuff like that to size here. And typically what we do is we would fix a number there on the heat exchanger. So we size them, based on the performance, but have like a 1 pound or 2.31 foot pressure drop across that. So we've got that known quantity to add in there after the fact, just to verify that we got the right pump size that we're looking for. So now we got the pipe sizing, 2 pipe sizes, low end and high flow, as well as the amount of fluid that we need for the system. We've got the pump sized up here now. Let's have a look at the expansion tank. So every closed loop hydronic system that you walk into is going to have something to basically allow for expansion of the fluid. So in a typical hydronic system, you get 2-3% of expansion in that system operating from, between, 60 and 180 degrees Fahrenheit, something like that. Much more expansion in a solar thermal system because you're really operating at, temperatures that are outside to maximum temperature in the summertime of this system, and potentially when it's in, in stagnation. So a very difference in temperature means there's a lot more expansion in your system. We also have to account for, in a solar thermal system, potential for steam formation in the collectors, which is going to push the fluid out of the collectors. And of course, the expansion tank is now going to be where all that fluid is going to be sitting, and it acts like a holding tank basically in a stagnation system. So if we undersize it, then we are actually going to have that relief valve open up. So the whole goal here is size the expansion tank, just like in a hydronic closed loop hydronic boiler system, that when the system is in regular operation, the boiler's not relief valve's not popping open and relieving the fluid. We want the same thing to happen in our solar thermal system. So the expansion tank acts as that factor when we're in those areas where there's no load, and of course we want to basically make sure that it's sized so that we don't have the relief valve releasing for us. So how do we do that? We've got another equation. So basically the size of the capacity of that tank is going to be a function of the amount of fluid in the collectors. We know that number, right? 9.45. This VD pipe is the amount of pipe work that would be subject to steam loads, which means when the collector here flashes the steam and the energy is still hitting it, there is potential for that steam to creep into the piping connected to the collectors here. So just to what degree, how many feet or meters of this piping could be exposed to steam formation. And that, of course, the more steam formation, the more fluids being pushed down into this expansion tank. So we have to make compensation for that amount of fluid to make sure the tank can basically accommodate that expansion. The other area we're looking at is just the degree of expansion. Just like in a regular hydronic system, the increase in the volume of the heat transfer medium in its liquid state. So as we heat it up, how much does it expand? So we know in the low flow system, we had 11.6 gallons, 15.1 gallons in the high flow system. And we need to know the expansion factor, which is part of the information that the manufacturer will give you. So we have a 0.13 expansion factor here, with 13% expansion rate change from -20 to 120 degrees Celsius. So pretty high rate of expansion there. We also have the, what we're going to add into our system as well is a seal. We're going to put some pressure on the bladder of the expansion tank, and it's going to have some amount of fluid already reserved in it. The reason why we do that is, of course, this system is expanding and contracting as it gets cold and hot outside. So if it really drops in temperature, of course, you're going to have that, the fluid basically requiring a bit more to top off. So some of your fluid in that expansion tank, as we pressurize, it will actually get back into the system as it gets colder and then move back in the expansion tank as it gets warmer. So there is a liquid seal that we add into a solar thermal system, and that's usually 4% of the system volume. So 21, you're adding in obviously all the fluid in that system, 21, a little over 21 gallons in the high flow, or low flow, I should say. I put high flow, that's low flow here, 21 on the low flow, 24.5 on the high flow. So there's a mistake. I went through this and I tried to find those little mistakes, and there's one right there. So I'll correct that before I put it out. And then we have this little pressure factor. So what the pressure factor is a ratio between the maximum pressure. So we're basically within about 90% of our relief valve. 87 PSI is a relief valve setting we send out on our pumping stations. 90% of that is about 78 PSI is our maximum pressure. And divided by the actual set pressure in the system. So for this application, we're going to set the collectors at 15 pounds here. And just remember that number, because we actually don't use 15 PSI with our we recommend a much higher pressure for our 200 FMs. You're going to see why in a minute, but I'll stick with a traditional one of 15 pounds here. And you're going to add to that the static pressure in the system. So this 2, right? The height difference between the pressure gauge, of course, and the top of the collectors. So 0.45 PSI for every foot multiplied by the 60 feet. We end up with a 42 PSI or so. Basically, we do all the math on that. The pressure factor here is 2.2. So what we don't have right now is the how much steam content in the pipe work that we're looking at, and that's going to be a function of how we pipe the collectors. So if you have a collector system where the collectors are at the highest point, A here, you'll see that what happens if we flash this collector to steam, it will push all the fluid out and it'll sit there dry basically. And of course, the dry steam is not transferring any energy to the fluid around it. Whereas in B, the collector is actually not the highest point, the piping is, and we get basically a pocket of fluid trapped in the collector. And now that has to boil off, of course, transferring that energy to the system as it boils. And of course, we're gonna have a higher steam production capacity if we have that little pocket in there. So what are we talking about here when we talk about steam is in closed loop hydronic solar thermal systems, it's potential where the collectors are gathering energy and you have no load, that you could get into a possibility of steam forming into your system. And it happens, it's been documented, it's been studied. We know how to work with it and how to utilize it, and basically reducing the occurrences of it and stuff is the goal of proper engineering. But if we have look at these two phases. This is kind of where we get into that steam formation, phase 2 and phase 3. So phase 2, if we have our collector positioned like this at the highest point, we go from phase 2 right to phase 4. If we pipe like this, we have basically phase 3 where we boil the fluid off in the collectors until it's basically gone. So the key here is basically how we pipe the collectors is going to dictate what that maximum amount of energy is going to be for that contribution of steam in our system. And then once the collector basically cools off, the whole idea behind stagnation is as long as we didn't pop the relief valve here and the expansion tank did its job, the system will just refill and it'll be ready to go the next day. So you basically, as far as the owner or the decision maker is concerned, nothing really happened in that system. They didn't have any evidence because we didn't lose any fluid, and things are just going to happen and kick off the next day without any particular issues. So calculating the basically formation of steam in the piping is basically the maximum steam output multiplied by the area in square meter or aperture area, divided by the heat dissipation of the piping. So that's basically the insulated piping. We use for inch and quarter pipe, somewhere around 31 watts per meter of heat loss can be assumed with an insulating pipe. Of course, if it's not insulated, it's going to have a much higher degree of loss there. If it's well insulated, a little bit lower. But for this purpose, we've got some documented numbers that we can use that you can look at in our manual. So I picked out 31 watts per meter on this one. So if we piped our collector, assuming we piped it in this configuration, but we'll do the math on both just to have a look at it. The amount of volume of fluid we'll have to compensate for possible steam in the lines would be the 60 feet multiplied, the 60 watts per square meter in this case, or 100 watts per square meter in this case, multiplied by the aperture area, so 15 times 2.32 or 34.8, divided by the loss of the piping. And you can see that we've got 65 meters, 113 meters in the one with the liquid pocket in it. So if we pipe this way, we're basically looking for 1-inch pipe. We need to add 9.2 gallons into the size nominal value of that expansion tank, 13.9 for the 1.25 inch. These are big systems, 15 collectors. So of course you're going to have some fairly large amounts of formation here. So putting those numbers together, hello.
We just wanted to interrupt you and tell you got 15 minutes.
Perfect.
All right.
All right. Perfect. All right. So we've got the high flow method here. We looked at the numbers. So 57 gallons in the high flow, 48 gallon expansion tank in the low flow. So if you compare about, the reason why we're saying low flow, you have more success is the fact that those components are going to be that much lower cost than the high flow. And we don't have an adverse effect on that system to that great a degree. So we're looking at the final thing here. We're getting into sizing up the pressure. We're going to set the pressure in that system. And this is where I wanted to go back to that set pressure at the collector. I said 15 PSI in the steam back calculation, but in our calculation, we usually use 44, 45 pounds for the collector. And for the expansion tank, we subtract about 5 PSI for it, more or less. And that basically allows for flexing of the bladder in the expansion tank so that we get that fluid volume already sitting in that tank. The reason why we want to look at the higher pressure in the collectors is if you look at the vapor pressure in Typhlocore, the antifreeze that we're looking at, remember the maximum temperature of our collectors is 145 C. So there's 145 C, and we get to vapor pressure at about 43.5 PSI. So if we're sitting at 44, 45 pounds in the collector, we actually never get to a steam formation in the collectors themselves, which means that we don't have that issue with, of course, the expansion tanks and all that. We still size expansion tanks because, there could be a leak in your system or something like that. And of course, we want to basically make sure we don't have a lot of, relief valve, issues with relief valve pressures, et cetera. So we still size as far as the tank to make sure that, your pressures are lower than that. But if we maintain that pressure, we don't have the issue with boiling of the glycol. Even if we did boil the glycol, if we look at the temperature that it boils at, 145, it's stable. Typhcore is stable up to 170 degrees C, which means that when it boils and comes back to liquid, it's still stable. We haven't changed the chemical nature components of that particular system. Even Dow frost, you can get down to 163 degrees or up to 163 degrees before it gets into some issues with it's evaporating and then coming back into a liquid as far as problems. So that's the difference there, is that we're going to protect our glycols and our system much better because we have that limiting factor. Remember, most of your flat plate collectors and evacuated tubes are going to be well above 190 C as far as stagnation, and there's just no way that you're going to be able to get that to stop going into steam unless you start rejecting heat, putting in components, expensive components, basically, to make sure that doesn't happen. So we're going to set our pressure at 44 pounds. You look at our static head here of our system. Remember, we got 60 feet of vertical distance, or that equates to 27 pounds of pressure as far as the static height here goes. We add those two together, right? What we should see here at our pressure gauge is about 71 PSI to know that we have 44 pounds of pressure at the collector. We have our system fill pressure here now. We're going to subtract 4.4 pounds, right, to get that, basically that bladder flexing, right? So when we look at this area, what happens is the bladder now can flex in the expansion tank. So we have that fluid volume sitting in there, so that little seal on our expansion tanks. We add a little bit of pressure in for the distance between the gauge and where your expansion tank's sitting. So 2 feet here, about another 0.9 we're going to add to our system. So overall, we're going to set the pressure in our expansion tank to 67.5, even though our system pressure is at 71 PSI. That's because we want that bladder to have a bit of flex on it. And then finally, like I say, as far as insulation, I talked about this a little bit and talked about the piping. So the more exposed piping you have here, obviously, the more expensive the system's going to get. If we don't insulate it properly, whatever energy we gather, we're going to lose to the piping here. If we have a lot of piping like you see here, of course, you got to insulate all that. You got to weatherproof it to make sure it's not going to be an issue. And of course, that adds cost to the system overall. So when I look at a system like this, if I can go to direct return instead of reverse return and reduce the amount of piping there and just add circuit setters, to me that, or flow setters basically, to make sure that each bank of array here gets a proper flow rate, that would be more advantageous to having all that piping out there when there's losses. Basically try to get the piping, exposed piping to a small degree as you possibly can, will help to basically keep the cost of that system down. But your typical types of insulation, one thing you don't want to put out there is, don't go to your Home Depot and buy that insulation you see for domestic hot water piping. That stuff will just basically melt when you get into those higher temperatures. So it's not made for solar. It's kind of made for more your potable systems, maximum about 140. Once you get up to about 90, 90 C on those, you start melting the pipe insulation. So, stuff that we use for typical boiler type of systems, insulation is what we'd look for. All right, so that's pretty much it. I just want to have a look a little bit at some systems before we stop. These we're going to review next week. So I'm trying to kind of tempt your palate here a little bit. We're going to be talking about these types of hydronic heating solar thermal systems. So the most typical domestic hot water systems that you will see out there are what we call preheat tank systems. So 2 tanks, 1 preheat tank. This is a solar tank. We call it the preheat tank. And then we have the actual standby tank or domestic hot water cylinder that provides the domestic hot water for the building. It could also be what we call a bivalent tank with the internal coil where the collectors heat the bottom and the boiler heats the top of it. Or you could have these preheat systems where we use an external heat exchanger instead of an internal heat exchanger. So those are typically what you would have out there. And they don't have to be hooked to a boiler necessarily or hydronic system. It could be a battery of direct fire tanks or whatever it might be in that building. The most common in retrofit would be this in residential applications. So we add a preheat tank to the collectors here, and we allow the system to run. So we'll have a look at this. Some of the issues with this might be the fact that, if you have a recirc pump on this tank here and you're recircing on a low load day, you're not actually drawing any water off here. This tank could be full of energy, but basically this tank might get dropped down in temperature where the boiler has to heat it, which is kind of a waste with this tank sitting here with a lot of hot water. You can add a pump to it, something like this. We'll look at different configurations like this to kind of add to the system. And what this would do basically is it would balance the temperatures between the tanks better on good solar days. It adds some capacity here now that the collectors can now add more storage because the temperature in this tank has dropped now that we can reheat it again. Pasteurization could be a possibility in those summer days where that's expensive to pasteurize a tank because you got to get everything up over 140 degrees. If the solar is doing it naturally, of course, we can just turn this pump on, and now we can disinfect both of the tanks simultaneously by turning that particular pump on. Some value there that we look at. So these are some, like I say, some of the things we'll be talking about next week. These tanks here, bivalent tanks, nice in the fact that usually they're pre-engineered, which means that you size the tank for what you need for domestic hot water for your building, because this boiler can only heat the top portion of the tank. That's the idea behind it. So typically recircs only come into the halfway portion of the tank. They don't come down to the cold side of the tank. And then of course the solar has the ability, because of stratification, to heat the whole tank on a good solar day. So the boiler is limited to 50%. The solar can do the whole 100%. And commercially, you can just add multiple tanks together here. And I'll talk about this one here a little bit more in detail as we move through. And of course, for domestic hot water systems and more commercial applications, sometimes instead of having a battery of tanks, it's better to have one larger tank, and of course, less piping losses, etc. But with these systems, you have two pumps. And these are fairly popular as well, because sometimes in some areas you might need a double wall heat exchanger, depending on what the inspector's looking for. And these are much more readily available out there in different sizes, double wall heat exchangers. We'll talk about those next week as well. Pool systems. You see a pool system here with a bivalent tank, a preheat system here. And the only thing I'll mention here is what we don't see, we'll talk about next week, is usually when we're using this boiler to back up the pool heating, we're going to put a heat exchanger in series with the solar heat exchanger here. So what would happen is when this pool water comes in and comes out, instead of going back into the pool, it would actually go back up. There'd be a sensor sitting there before it goes into that boiler heat exchanger, plate heat exchanger. And if it's not hot enough, the boiler can come on now and top up whatever it needs before it dumps back into the pool again. So I'll have a schematic for that to show you what it looks like when we get into that particular application. So the same kind of idea, using basically a tank like this. This could actually be not just a domestic hot water system. Maybe it's maybe it's a space heating system. So we heat the pool in the summer, and then we go to a buffer tank here and we heat the building in the wintertime or something. So there's some flexibility in our piping arrangements as we move through. A space heating system we talked about and the challenges with that. You see the tanks are a little bit larger in size. The whole idea here obviously is when this return water comes back, if we can basically bypass the boiler and go right into the tank here for usable heat, now we're starting to contribute some energy into that system. Some lower cost systems might be this. We've done this on occasion too, is what we call kind of like an after heat function, where instead of, like a low solar fraction, those shoulder season type of spacing applications where we charge up the tank, it gets up to a higher temperature than what we actually need for domestic hot water. And we can turn a pump on basically and pull this excess heat and dump it into the boiler side of your system here. So not a lot of extra components here, and we're just utilizing whatever extra heat is being made by the system to dump in to get a bit of fraction into that spacing system. So not a lot of extra cost, virtually none, but a little bit of benefit for the spacing side of your systems. So we're going to talk about those in bigger detail. I just want to kind of give you a little taste for what we're dealing with next week. It'll be more on those startup, programming of the systems, some commissioning information, identifying system problems to avoid, things like sensor locations misplaced, those types of situations. So we'll kind of cover all that stuff, and that basically will take you from start to finish of a solar thermal system over these three seminars. So I hope you found it informative. So I'm going to ask Mark right now, do we have any questions?
No open questions, sir.
No questions. And look at the time, Mark.
You're ahead. Like you're just lightning today.
I'm on fire. Yeah. Solar and on fire. Perfect. Well, that's like I say, the end of this one. We have one coming up next week, and we're going to have this one archived here shortly. And I think you said, Mark, in a couple of days, the last week's will be available for you too as well. So
Yeah, I would think she'll have it up by tomorrow.
lovely, wonderful. So we have any no questions?
No questions. We're good.
Okay.
All right.
Well, thanks everybody for joining us. Always a pleasure to have you guys join us here. We have a good time putting these things together for you. We just hope that the information is working for you. So if you have any questions or comments, certainly you can reach out to us as well, and we'll try to answer those questions if you have something that you kind of think about later on today. But until next time, I again have a pleasure of speaking with you guys today, and hopefully you can join us again next week for the final installment of our solar thermal training. Thanks so much.
Thanks, guys.
Bye-bye.